Welcome, class. What we're going to take a look at today is actually from section 3.6. It's derivatives of both exponential and logarithmic functions. So go ahead and get out your notes, and we'll take a look at what these are. In this section, again, we're going to figure out two things: how to differentiate an exponential function and also how to differentiate a logarithmic function. So we're going to start with the exponentials. So for derivative of exponential functions, remember, exponentials, we're talking about some base number raised to a power that's a variable. Okay, so a would be an actual value, 2, 10, anything. And then our exponent is the variable here. So for our derivative, the derivative of an exponential function, which I'm just going to use a to the x, equals a to the x times ln a. Okay, now remember, we already talked about the derivative of e to the x, okay, which I'll show you below. All right, so derivative of e to the x, we said was just e to the x. Okay, well, it actually still fits the model above, because if we use e to the x times the natural log of e, remember, natural log of e actually equals 1. So that's where we get the e to the x function spit back out. Now, if the base is not e, if it's another number, like 2 or 5, we do have to tack on that little extra piece of that natural log of the number. Okay, so let's take a look at a few examples of what this looks like. For example number 1, we have y equals 2 to the x. So if I'm finding y prime, I'm going to start with the derivative, or the actual exponential again. So it's 2 to the x multiplied by the natural log of the base, which in this case is 2. Okay, and then that's our derivative. In terms of how you would write it, you can put the natural log of 2 in the front if you would like, or you can leave it as it is here. For now, I'm just going to leave this one as it is. Okay, number 2. All right, now this one is not just 5 to the x. It's 5 to the x squared. And as soon as you say, okay, this is not just a general exponential anymore, I have something other than x up there, that should signal that we need to use the chain rule for this one. So what I'm going to start with is 5 raised to an exponent. That derivative is 5 to the same exponent multiplied by the natural log of the base. So natural log of 5. And then I'm going to apply the chain rule here. I need to do the derivative of x squared. So I'm going to multiply this by 2x. Okay, again, in terms of rewriting this, we can put the natural log of 5 and 2x in the front. But for now, we're just going to leave it as it is so we can clearly see where that derivative comes from. Okay, so if you want to make a little note, all right, this 2x came from using the chain rule. All right, last example. We have 4 times 3 to the power of x. So when you're looking at an example like this, make sure you know what the base is of your exponential function and what would be considered, in this case, a constant. All right, so 3 is the base of our exponential function, while 4 is actually just a constant being multiplied in the front. Now, when we have constants being multiplied, remember, they're not going to affect our derivative in terms of finding it. We're just going to multiply by them in the end. So y prime is going to be 4 times the derivative of 3 to the x. So that's going to be our new formula here, 3 to the x times ln of 3. Okay, here, again, you can rearrange a little bit, but nothing can really be combined. We would just have 4 ln 3 times 3 to the x. We could do a little bit with some of the log properties, but for now, I'm just going to focus on finding that initial derivative. Okay, so the next thing that we're going to cover is the derivative of logarithmic functions. Okay, so as you see in the box there, we have derivative of log base a of x, and I'm just going to show you what this derivative is first. We end up with 1 over x times the natural log of the base. Okay, so I'm just going to show you a little proof of where this comes from using what we just learned with the exponential derivative. For this part, you don't have to copy it into your notes. You can just watch and follow along, and hopefully it'll make it a little bit easier to remember what the derivative is after seeing this. Okay, so let's recall what we just talked about. So we know that the derivative of an exponential, I'm going to use a to the x, equals a to the x times the natural log of base a. Okay, so now let's take a look at our log function. So I'm going to make a little more room here. Okay, so I know that if I write my log function, base a to the x, I'm going to say that that equals y. So I'm now turning this into a function. Okay, because logs and exponentials are inverse functions, I can use that understanding to rewrite this in terms of an exponential. So this is equivalent to a to the y equals x. Okay, those were properties you learned about last year, switching between exponential and log functions. All right, so now I have an exponential function, which I already know how to find the derivative of. But because I have more than one variable, I'm going to use my implicit differentiation. Okay, so that means I'm going to end up with those y primes in my derivative. So I'm doing the derivative of ay and then the derivative of x, because I have to do derivatives on both sides. Okay, so derivative of ay, I go back up to my exponential derivative there, and I see it's going to be ay, a to the y power, times the natural log of a. But remember, this is implicit, so I have to multiply by the derivative of y prime. Okay, that comes from the chain rule, since my exponent is not an x, it's something else. Okay, on the right side, the derivative of x is just 1. Okay, so I'm going to solve this for y prime. Let me make a little more room here. So all I really have to do is divide by ay times ln a, which is all one term, or all connected because they're multiplied. I'm going to do that on both sides. So I end up with y prime equals 1 over ay times ln a. All right, now remember, y prime, if I look back up here, y is log base a of x. So this is the derivative of my log function. So I can actually say that y prime is the derivative of log base a of x. Now, there's just one problem that's remaining here, is that I have this derivative in terms of a y, and I want to keep it so that it's in terms of an x. Okay, so I'm going to do another recall. Y, as I said up above, is log base a of x. So I can replace that now in my derivative. Okay, so instead of 1 over a to the y times ln a, I have 1 over a to the log base a of x times ln a. All right, now last thing here, because I have base a raised to log base a, there was a log property, and I'll put this over to the right as well, that says when you have the same exponential base and same log base, they're essentially going to cancel each other out, and that's equal to just x, or whatever's in that log function. So replacing that, I end up with 1 over x times the natural log of a, which was, if I go back up here, the derivative of the log that I was looking for originally. Okay, so this is a proof of where it comes from. Again, that was just to help you remember it a little better. So now we're going to take a look at some examples. Okay, so we're finding y prime. Feel free to try these first. Pause the video and then come back and look at the answers. All right, so first one, y equals log base 2 of x. So I know I'm going to rewrite my derivative up at the top here. The derivative of the log base a of x equals 1 over x times the natural log of base a. Okay, so here I have a base of 2. So when I go to find y prime, I'm going to get 1 over, now x is still an x, it's what's inside the log function, times the natural log of the base, which in this case is 2. So I have 1 over x times the natural log of 2 for my derivative. All right, second example, log base 5 of x squared. Again, now I have to consider that this is not just doing the derivative of a log, but it's also going to include a chain rule because that's not just an x anymore. Okay, so I'm going to start with my log derivative. It's 1 over x squared, that's what's inside the log function, times the natural log of 5. Okay, so that's just using my log derivative. But now I'm going to multiply this by the derivative of x squared, which is 2x. And again, there's where my chain rule came in. Okay, I can simplify this a little bit. Y prime can be written this way, 2x over x squared times the natural log of 5. Cancel out an x in the top and in the bottom. And I end up with 2 over x times the natural log of 5. Okay, one more example for today. So I have y equals 3 times the log base 3 of x. Okay, this 3 is a constant out front, so I'm going to multiply it to the derivative of my log. So I have y prime equals 3 times derivative of log base 3 of x is going to be 1 over x times the natural log of the base 3. And then multiply that to my constant. All I'm really going to do here is rewrite it. 3 over x times the natural log of 3. Okay, what I'm going to do is show you a few more examples. Okay, so for these we have 3 different functions, f of x, and we're going to use our understanding of this log derivative to find the f prime of x. I'm going to have you try these on your own, and then we'll start with the answers to these at the beginning of class so you can take a look and see how you did. Now remember, always pay attention for those other rules that come in, chain rule, product rule, or quotient rule. In all 3 of these examples, you will have to use at least one of those rules, if not more than one, to come up with your derivative. Okay, so good luck on those, and I will see you in class.